So we have this polynomial g of x. It's in the upper right-hand corner. And then we know, from what the book tells us, we know that one of the zeros is 5 plus 2i. And what we're being asked to do for this whole problem is we're supposed to find all the zeros. So just looking at this problem, what else, if anything, can you tell me? Or how could we even go about starting this? Do we have any thoughts at all? Emma?
So if your imaginary number zeros are would you say that one of the other zeros would be 5 minus 2i?
If the imaginary or the complex zeros always come in pairs produced by the quadratic formula, can't we then make the statement that this is a second zero? So if they give us one complex zero, they actually give us two zeros. Which means, how many zeros are we still looking for? Just one. And at this point in time, we know it has to be real because of what Emma said. Complex zeros come in pairs. So if we had two imaginary and we have three total, the other one is real. So I want you to think for a second. So what could we try at this point? Dawson? We could graph it in our calculator and just try to find that real zero. Positives? It's easy. Negatives? Requires technology. It won't find perfect solutions. You know, what if it's actually some crazy root? For this one, it won't be. But what if it was some crazy root? It actually won't find that. It'll give us a decimal approximation. So there are some downsides there. What other ideas do you have? What else could we try to do to find that third zero? Okay, so here's where I interject. If I know what two of the zeros are, I really know. If I take g of x and I factor it, I know what two of the factors look like. One of the factors looks like this. You know, x minus the zero. So we know the relationship between the factors and the zeros. I know the other zero, one of the other zeros, or one of the other factors, sorry, looks like this. And what we're really trying to figure out is, what's that third one to make g of x? Questions on what we just did. So ideas, how does this help me? How could I keep going? Larissa?
You could just box those, factor those part of it.
Yeah.
The area model.
So we could distribute out the purple and the blue factors. We could use the area model or whatever other distribution method we want to kind of reconstruct a part of g of x. When we do that, what's that going to look like if we multiply out that purple and blue factor? What is it going to look like after we've done that? Like, don't tell me the actual, like, hey, it's going to be exactly this, but what is it going to look like? Yeah, we're going to build a quadratic. So we're going to end up having some quadratic piece that's going to be here multiplied by that one linear factor that we're still looking for. Okay. So if we're gonna multiply those out, or we're going to distribute those out, what might, and Larissa's saying, hey, that the area model would be great here, right? What do you want your area model to look like to multiply those out? And there are two schools of thought here. One, I could make it a 2 by 2, right? We can say x, and then we could say subtract 5 minus 2i is all one big chunk, right? And we could say x, and we could say subtract 5 plus 2i. that's kind of annoying because then I have to multiply those two complex numbers, and some people don't like that. I don't mind it. Some people don't like that. So another way I could go about this is I could see it as a 3 by 3. If I go ahead and distribute that negative. So really that purple one is going to become x subtract 5, and that subtract negative 2i would become plus 2i. And then for the teal one, we'd have x subtract the 5, and then it would be subtract the 2i because we distributed that negative. So either the box on the left or the box on the right, sorry I didn't stay consistent with colors, we do this. Actually, hands, who would like to use the box on the left? Who would like to use the box on the right? All right, there it goes. We'll use that one. So I'm going to get x squared here, right? We're going to get subtract 5x here, maybe. We're going to get plus 2i, x. We're going to subtract 5x there, and subtract 2i x here, plus 25, subtract 10i, plus 10i, maybe, that's an I. And then we're going to get subtract 4i squared. Now, it looks kind of hideous, but what do you notice that's nice about this? Yep. Which ones? Opposite? Opposite. And that's that whole idea of like those complex numbers were conjugates, right? So those parts are going to drop out. All the imaginary parts actually drop back out because what's negative 4i squared? 4, which is kind of nice. That's just a 4, which means when we multiplied all that out, we ended up getting x squared subtract 10x plus 25 plus 4, so really plus 29. And that came from the purple and blue. I'm going to erase that area model so I have some space. And we know that that, multiplied by that last linear factor that we're looking for, would really make g of x, that polynomial that's still up there on our right. So knowing 1, 0, we got a second, which was great. We're able to build a whole quadratic out of that if we just distribute that out. So how could we keep going? In what ways might we be able to keep going and find that other linear factor? Yeah, and I think for this one, that's really how I would go about this too. Since a cubic's relatively small in terms of its degree, once we know that quadratic, it's pretty easy to get the other parts. So, I'm just going to start with those things that are easy to build. And from that, we can see that this has got to be x, and this has to be plus 3. And if we filled in the rest of the area model, it's going to work, which is awesome. So the area model is a nice organizational structure to factor. Questions on that? And if I just carried that out, there's my subtract 10x squared, and here's my plus 3x squared. Important because we realize that makes our negative 7x squared that we have up in the g of x. This would be my 29x, and this would be negative 30x, which gives me my negative 1x. That's up there. And so we can see everything works out really nicely. All right, so that would work. Anybody have any other thoughts? Again, I would use that for a cubic because it's small, in terms of order, and it's pretty easy to use. Any other ideas? Dawson? What would the quadratic formula do for us? The other option here, and I'd really only use this one if it was really higher than a cubic, right? If it's hard to get that last one. I can use long division. So I'm dividing x cubed, subtract 7x squared, subtract x plus 87. And I'm trying to divide this by my green one, x squared, subtract 10x plus 29. And so if I'm going about dividing this, I really look at how many times does x squared fit into x cubed? Or what would I need to multiply it by to make it x? And so then if I multiply that x by the x squared, I get my x cubed. It made that x multiplied by negative 10x squared. Or sorry, negative 10x would make negative 10x squared. X multiplied by 29 would make my 29x. So the black is what I'm trying to make. The pink is what I've already made. Keeping in mind that long division process, I can just now subtract. And so I realize that what I still need to make, what I have left over, the x cubes dropped out. Negative 7 subtract negative 10 is 3x squared. Negative x subtract 29x, negative 30x. Bring down my 87 because I still need to make that too. So then I have to think, okay, so x squared, I'm going to divide again, right? So I'm trying to figure out x squared goes into 3x squared how many times? 3 times. And if I multiply that 3 by that green stuff, the stuff I'm trying to divide it by, we made 3x squared, subtract 30x, plus 87. We subtract those two, because the black's what we're still trying to make, the pink is what we've already made. We get nothing, realizing that it divided in perfectly. That pink factor multiplied by that green factor made all that stuff in black. And so we could figure it out that way. For me, I wouldn't use this, again, like I said, in this case, because it's really easy to get that last one. But think about if the thing that we're dividing is really like a 4th or 5th degree polynomial, something that's harder to kind of factor out with an area model. Long division will still kind of process through it for us, which is nice. What questions do we have?